I would also like to thank the organizers of this school for inviting me. It's great to be here and to talk about some, I will actually talk about some foundations of quantum theory. That will be one part, and the other part will be about thermodynamics. So the structure of the course will be such that the first 2 hours will be devoted to understanding essentially what the wave function is. This is, of course, a very basic topic. It's also an old topic in physics, as I will explain you. And then the other 2 hours will be about the connection between quantum information and thermodynamics. We will see that from quantum information we can learn a lot about thermodynamics. And I should also stress that in both of these topics we'll see somehow a more theoretical part that is in some way purely conceptual, and also some applied parts. So when I talk about the meaning of the wave function, this is not only some philosophical issue, there will actually be theorems, but also it has applications. As I will explain, this will be interesting for example, random number generation, or also for quantum cryptography. And I would say it's not only interesting for that, it's even essential to understand the nature of quantum theory in order to make precise statements about the security of quantum cryptographic schemes. And also in the other part, when we talk about thermodynamics, I will talk about applications. I mean, first about theory and then applications. And applications will have to do with the question, for example, how much heat or energy I need in order to drive a computation. We saw just in Scott's talk that energy is a limiting resource, and we will talk about more kind of precise statements about how much energy is consumed by individual computational steps. And as I said, this will be for the second half of the week. So I will talk today about foundations, and I will somehow start by giving you an overview and motivate the questions. And some of these questions are very old questions that date back to the early days of quantum theory. Some of them have been asked, for example, by Einstein in letters that he wrote to colleagues like Schrödinger. And there are also some more recent versions of these questions, or more precise formulations. And I think the amazing thing is that today we have theorems that answer some of these questions in a very precise manner. So while the questions may appear to be rather philosophical nature, we now, and I think this is thanks to quantum information, have a good understanding of how to make these things precise. And then tomorrow I will go into more technical details. And as you will notice, or at least that's my experience, when you talk about these like foundational issues, it's always a bit confusing because there are many conceptually difficult parts in it. So tomorrow I will give again an overview, kind of summarizing what I do today. So if you have some troubles today, then it may be clarified again tomorrow. So it's in other words, it's something that you may need to hear twice in order to really understand all the concepts. But I would also like to encourage you to ask questions during my talk. So I don't have a fixed schedule. There is plenty of time for questions. So if you feel that you don't understand something, please ask immediately. So let me start by motivating this question. So what we have in physics, and I would like to draw this table, is first of all we start with experiments. And of course then we have a theory that tries to somehow explain what we see in the experiments. You see, this is now not a computer science talk, it's now a physics talk. And there will be laws, and not only conjectures.
I have laws too.
Okay. So what do we see in the experiments? So in the experiments we just have access to certain devices, and at the end, if you have a theory, you really want to, I mean, and that's the concept behind all what I'm saying. It's all supposed to be at the end operational. So all statements we want to make should be experimentally testable. And so the question is really, what do we have in the lab? And clearly in the lab, no one has ever seen a wave function. So on this part of this table, I will never write down a wave function. This is something that only appears in theory. In the lab, we have knobs and we have screens and displays and pointers. So what we, for example, do, let's say on a more abstract level, we somehow turn certain knobs in certain positions. And so this I call, for example.
But is not the knob itself a theoretical construct? Right.
In some way, yes.
You don't have to answer that.
Actually, that's a good point. I mean, everything, if I draw things here, that's of course already on a huge, on a very abstract level. So I make an abstraction of the actual experiment. But I think it's clear how to draw a knob. I mean, even I as a theorist know how to turn knobs. Usually I destroy the experiment by doing so, but at least I know how to do it. And then we can, this is the even more unproblematic thing, we can read off certain numbers. For example, we have a display and it shows that there's a certain voltage on the device. So this is something that is displayed somewhere at the end, usually in today's experiments just on a computer screen. And something happens, of course, here in the middle. Here's some experimental device. And now what we do at the end usually is that we choose several positions of the knob and we repeatedly read out our displayed thing. So the knob position could, for example, be the strength of a beam at LHC at CERN, where you do some colliding experiments, and then this is what the detectors give you. And at the end, you collect statistics, and statistics could be expressed, by kind of a probability distribution. That's a way of writing it. Of course, that's defined by the frequency, and I will use this notation to write down conditional probability distribution. So what this is actually a function. Maybe I should define that. So this is the name of the function, which says it's the conditional probability of x given a, and as arguments to the function I have here x and a. So what that means here is that these capital letters are random variables. So random variables can of course take values from a set of values. Usually we'll consider a discrete set of values, and small letters will be used for specific values. So this means it's the probability that the random variable x takes the value small x, conditioned on the event that the random variable a, which is, for example, here the knob position, takes the position small a. So that's just a notational thing. Please ask if this is unclear, because I will use this notation all over my explanations. Now, here this is defined via frequency. So I just repeat the experiment, and so this is statistics that I take. But this is really something that doesn't follow from any theory. There are also no assumptions. You could, of course, say, in order to make a statistics, I make assumption that I can repeat the thing independently, but all statements I'm going to make will, of course, be theoretical statements. So this is just something I can do if I'm just doing the experiment and write down things and do maybe some calculations to summarize everything. But now, of course, there's also some work for the theories. The theories now try to find some pattern in these statistics. And the pattern, of course, what we could do as theorists is just to write a huge book with all possible patterns that we have ever observed. That will, of course, have a huge complexity, and it's, of course, a desire of physicists to reduce the complexity of the description of nature. But in principle, you could say nature is described if you have all tables with all frequencies that we have ever observed. But then, for example, we couldn't make predictions about future experiments. So what the theorists would like to do is to understand this probability distribution, and understanding on a maybe complexity theoretic level means to bring it into a form where it's simple. Simple in a, maybe you could think of Kolmogorov complexity. There's a simple law describing these probabilities, and then from this simple description be able to infer about future experiments. So we want to have a rule that allows us to say what happens if we now choose another knob position that we have maybe not chosen before, or maybe we chose it once, but maybe have different knobs, and we have a new combination of knob positions, and we want to predict what is the frequency. So that's what the theorists want to do. And in order to do that, they do a lot of work, and what comes out is, for example, quantum theory. And so what is quantum theory? Quantum theory has, of course, certain additional objects, like the wave function. That's, of course, not the whole theory, but this is an object that appears in the theory. And then we have also, for example, descriptions of measurements, like maybe I write them as pi x comma a. So these are measurement or projectors, measurement projectors. So mathematically, of course, this wave function is just some unit vector in a Hilbert space. That's what the theorists say. And then also this measurement should be such that for all a, so a is kind of the choice of my knob position, and for all possible positions of the knob, it should be a quantum measurement, which means that, for example, these projectors pi should add up to the identity on this Hilbert space H. So these are kind of elements of the theory, and at the end there should of course be a connection between the theory and experiment. So what the theorist says is that there is a rule. He can now write down what this frequency is, and the rule is of course what we know as the Born rule. In this particular case it would be written as, I mean, one way to write it is this. And you see, this makes the actual connection. So we have here different objects. We have this pi and we have these measurements. And here we have experimental observations. And the connection between theory and the experiment is made via this Born rule, which tells us how these purely theoretical concepts relate to the experiment. And now, you see, what from the explanation I gave now, there's nothing special about the wave function. It's just some mathematical object that allows us to state the rule, which then hopefully corresponds to what we observe. Nevertheless, as physicists want to understand this better, or they want to make stronger statements. And if you compare, for example, what I've written down here to older theories like classical mechanics, then the connection between experiment and theory is much more straightforward. So in classical mechanics, you have what you observe are, for example, positions of particles, and the theory really talks about positions of particles. And so you don't even actually explicitly distinguish these two things. It's just the theory is so closely linked to the actual observable quantities that you don't make consciously this conceptual distinction. But in quantum theory you have to, because as I said, you will never see this wave function on this side. Yes?
In this theory side, you are confining a particular interpretation, right?
Yes, I mean, I'm now giving, okay, maybe I should, thanks for the question. I should stress that, of course, I'm not trying to be as general as possible. I'm just trying to give an example of what a theorist would say about such an experimental situation. And of course, there are now many questions, and indeed, there are also many equivalent ways, even in quantum theory, to describe what I've seen here. Just maybe to mention one equivalent way. You could say, this is actually a question that is not answered by physics. Why is A parameter to the experiment and not something like a state of a system? I could also take a different use, actually an alternative. Maybe I write that down just to be clear about what I want to say. Someone else could describe the same experimental setting in quantum theory and say that there's a wave function psi bar, and this wave function, for example, is something of the form psi, like here, tensor something else that I would maybe denote with a vector A, which carries the state of the knob position. So instead of saying that the knob position is just a parameter to this Born rule, it's itself a system, like there's a knob, and this is a system, and this has a state. And now the Born rule would look different. I would now define another measurement operator, which in that case could, for example, have that form here. I would sum over all A, and then take the tensor product of A, and then say that my Born rule, Px given A, is now, or maybe I would write it like that, the joint probability distribution of X and A is now given by psi bar, and then this other projector, this still depends on X, by the way, because I only summed over A, and psi. So this would be another way for describing the same setting, where I somehow make a conceptual take a conceptually different approach. Now I said the system, so this is also somehow a system with a state, and this state evolves to that. And there is and this is actually something you have to be aware of if you learn quantum theory. In quantum theory, if someone tells you, analyze this system, there's kind of seems to be a common understanding of what is the system, and what are the parameters, and what is the measurement. But there is no way to define that. So if I analyze this chalk, no one tells me what is now the system and what is the measurement. Because I could, for example, take the system to be everything, like including the process how I look at the chalk, or I could take the system as just the individual atoms here. And there's no rule in quantum theory that defines that. Nevertheless, in usual, let's say, textbook problems, we usually have a particle in a box, and the box is the system, and the particle is the degree of freedom we look at. But there's no rule. So if you just, I mean, this is something one has to be aware of. Quantum theory doesn't give a receipt of how to analyze a real physical experiment. And even if you go to a lab, this is completely unclear. You may take the laser that steers some ion as part of the system or as an external parameter. But the important thing is that you don't need to decide on that. Quantum theory should be correct independently of how you apply it. And this is just an example of that. Now I had two different descriptions of the same physical experiment, taking different views on what is the system and what is the parameter of the system and so on. Okay, is that? Okay. Okay, now what is the question? So the question people now are asking since a long time is there also a more direct relation between this wave function, this object you have in the theory, and the experiment? So in some way the question is the wave function more than just an experimental description, or is it more than just a mathematical object that allows us to write down these conditional probabilities in an elegant way? And so you can now ask, what does that mean? And one way to somehow explain what that could mean is the following. The question is, if, let's say, someone didn't know about quantum theory and would independently derive his own theory. Let's say you had some other civilization that sees the same, can do the same type of experiments, but of course they would come up probably with a different theory. And now you could ask, they will probably also have some objects in this theory. And you could now ask, are these objects somehow the same objects as the wave function? Is there a one-to-one relation between the objects you have in another theory, which may be other objects, not elements of a Hilbert space, could be some other mathematical object, but maybe there is still a one-to-one relation between the two. Maybe it's just a different language. And if this was the case, if for any other theory you could kind of map the mathematical objects to the mathematical objects of different theories, this would mean that there is more meaning to the wave function. This is what, and I will explain that in more detail, this would means what some people call the wave function is real. So some people say the wave function is more than a mathematical object if it's in some way unique. If in any theory you would come up with, you would somehow end up with an object which is in one-to-one relation to the wave function. So this was now not very precise, but I will make that precise in a minute. But you see, there is somehow this question of how does this relate to this. There are now different levels of this question. So we could, for example, ask also, is it possible that you have another theory which somehow provides you more information about these measurement outcomes? That could also be the case. And this is also a question you wouldn't ask in any classical theory. Because in classical theory you have this one-to-one relation. And here you could still ask, maybe if you had more information about the system, maybe we can make more deterministic statements than the type of statements we're currently making with quantum theory. And these are all questions that I will now try to make precise and formulate as mathematical statements and then show you how we can somehow prove theorems about them. Yes?
When you say if you get some more information from theory, it's by analyzing the same parameters of the experiment. Like you're not allowed to start taking into account things like, I don't know, the weather or whatever.
Yes.
Yes.
Yes, I mean, it could be, of course, I mean, here I've made somehow an implicit step. So, of course, this psi will be different for different systems here. So, of course, it could be that so in order to, I mean, somehow I also need to have a relation that tells me, given an experimental setup, what would be the psi. One way to do is to say, just make the experiment and try to find the one psi that actually gives the right function here. So that's the way one would do it in the lab. But at the end, you have somehow a relation between what's here going on and psi. And it could now be that another theory needs more details about what's going on here and then can make more precise statements about what's going on here. And maybe in short, the answer will be this is not the case. So maybe I should, as an outlook, so after these first two lectures, you will see that in some way the quantum mechanics is quite unique. It's every other theory that you would come up with either has some extremely unnatural properties, and there will not be many properties. There will not, I mean, this will just be like essentially two basic properties. Or if it doesn't have unnatural properties, it will actually be equivalent to quantum theory. And that's the content of many of the recent results that you may have seen. For example, there has recently been a kind of a hype about a theorem called the Ppr Theorem. And the content of this theory is exactly a statement of this type. So the Ppr theorem will tell us that if you have another theory, this other theory will still determine the wave function uniquely. And I will also tell you what that means. Okay, so let's now move on and make these things a bit more precise. So for that, I now just erase this part, maybe. And I already indicated that in order to make statements about how this relates to experiments, in order to make mathematical statements, we should somehow about the theory. One elegant way to do it is to talk about alternative theories and show how they relate to each other. So the approach that is now taken is that we have here, so this is now quantum theory, and here we have some alternative theory. And the way you should think about this alternative theory is really that if you had another civilization that would come up with some theory that tries to explain experiments, they would come up very likely with a completely different formalism. But they will also have probably some object. That's, of course, now an assumption. But assume they also have some mathematical object, which we call lambda, which somehow depends on internal parameters of the system. So in the same way as we talk about the wave function in quantum theory, there is probably some parameter in this theory. So this is just a parameter, or some, maybe I call it a variable. It's some variable. And then, of course, in this alternative theory, we'll also have a rule. And the rule will be a rule that tells us what is the probability of observing a certain outcome if we have a certain knot position and also conditioned on this variable. And maybe to make now things look a little bit more similar, let me now simplify this setting a bit and talk here about the same way in quantum theory. So what quantum theory actually does, what I told you before, it on the abstract level, it just provides us with a rule that tells us that we have the object, so the variable, this is the wave function, but wave function is just on an abstract level some value. It's a value, and given that value and knowing the knot position, the Born rule tells us what is the probability distribution of the outcome. So I call that again the Born rule. It's the rule that I had before explicitly. So you see that there's the same pattern. So, and this is the only way, or the only thing I mean when I now in the following talk about theories. So by theory, I just mean something that has a parameter and a rule that tells us, depending on this variable, what are the statistics. And I'm not claiming that this is a good definition of what a theory is, but I'm claiming that whatever theory you have, it should at least contain these elements. So whatever physical theory you have, it should give you a rule that tells you what you will observe. Otherwise, it's not an experimentally testable theory. So it's kind of a minimum requirement to any theory that there is such a rule. Yes?
The symbol P, X, and A meant something. So the
Yes.
probability of X given A.
Yes.
So,
Okay.
But psi didn't appear because that's
Yes.
in the definition.
Yes, thanks for asking. That's very good that you are. So maybe let's start here. So here this is, in the alternative theory, I would just say lambda is a variable. So now what I didn't say and should have said is that let's now formally just assume that all these objects are random variables. So I have a random variable. I mean, this value may, of course, be constant for a fixed preparation of the system, but I may also have a theory in which I can choose the parameter. And so let's assume this is a random variable. So it's a value that I can choose with certain probabilities. And also the knot position can be modeled as a random variable. Of course, it may be hard to determine the distribution, but I don't have to because I'm only conditioning on that. And the outcome is a random variable. So I have formally, in a mathematical sense, I have just 3 random variables here, namely x, a, and lambda. And now I'm talking about the fact that the theory will define how the outcome random variable will depend on the other values of the random variable. So just mathematically look at lambda as a random variable.
I mean, I thought you were very careful to make a distinction between A and psi, where A is something that has physical reality.
Aha, yes, okay, that's a good. Aha, yes, that's right. So, and here I do the same thing. So here I say the wave function may also be something that takes different values, and it's also a random variable. So it's true that both the things that I can observe, a and x, are random variables, as well as psi is now modeled as a random variable. This doesn't mean that I can also observe psi. So I really want to make a distinction between a, x, and psi, but this doesn't prevent me from saying that despite that psi is something very different from x, I can model it as a random variable. It's a value I can choose randomly. So I'm saying that it's a random variable doesn't imply anything more than that there's a probability distribution defined on them.
But I would have said once you know the probability distribution for psi, you can compute the probability distributions for a and x.
Yes, that's...
And so then
no, not of a, maybe.
The same,
I mean, that's right. So it's almost right. So if I know the probability distribution of psi and of a, I can compute the probability distribution of a, x, and psi. What I'm saying, however, is that psi is something you cannot observe, whereas a and x is something you can see in the lab.
Are you saying if psi is the wave function of the whole universe, then it determines psi and x?
well, yeah, I might be inclined to say that. That was sort of his theory prime. But,
I see, okay.
Yes. But, okay, so the important distinction is that psi is something I will never observe in the lab. So I have to make statements about psi without ever having access to it. But what I have is a relation between the theoretical object that I cannot observe and variables that I can observe. And the relation between the two is given exactly by this rule. So this is the whole purpose of this thing, is actually to make a connection between a non-observable quantity and an observable one. So at some point, I have to have a mathematical object that includes elements from here and elements from here. And that's exactly this thing. That's this rule that tells me I have here non-observable objects and I have observable ones, and this rule somehow connects them. It says, given the non-observable ones, how are the observable ones connected to that?
Right, well, I know what you mean. I was just a notational complaint.
Yes, okay. Yes. So maybe the notational difference is that non-observable things will be in Greek, will be Greek letters. So that's maybe the way to remember. But they will all be random variables. So. Okay, and the same is true here. Now, okay, yes?
So is there,
sorry, yes.
is there an experimental equivalent to P of x a psi? So if you were to take this P x a psi, is there just P of x a in the experiment common?
You mean, I'm not sure I really understood the question. So,
could you write P of x a under experiment, and is it the same?
P of x given a. Yes. Or, yes.
Is that the same as P of x?
So if I, okay, we will just, I will come to that point. Okay. The question is, when do we choose the wave function? So is it something that is just fixed for the experiment? And if it's fixed, then we will just here observe we will have here the statistics of x given a. We could also, of course, consider an experiment where we prepare the system differently, and then there will be different wave functions. And what I wrote down now is general because the wave function psi is now a random variable. So I'm prepared for what I'm going to do, namely to consider different preparations of the system. Yes?
So are temporal issues in dynamics being ignored for simplicity? Or?
No, yes, I mean, now I didn't talk about dynamics, but this is just part of the rule. So if you have here some, let's say, if you have a system where there's some dynamics and then a measurement, then there's, of course, still the Born rule valid. I just have to apply the Born rule to the evolved state. But I'm not excluding any dynamics. I just didn't write it down explicitly. But there was a question there as well.
In our analytics theory, we are already assuming that there
Yes.
But is it trivial? Is it the most general way? Because, for example, if we even give up the causality, then we do not necessarily have the object, mathematical object with all information, because we cannot really separate the state from our measurement, right?
Yes.
So what is the scope of this alternative theory?
So this is really an excellent point. I think this is actually I mean, I wanted to come to that in the discussion later, but let me already say now that there is kind of a hidden assumption in what I'm doing here. And the hidden assumption is indeed that the theory has certain classical objects which describe nature. And it's not at all clear that this exists. It could be that that nature is such that we cannot write down laws on a piece of paper classically, that somehow the laws are themselves quantum objects. I mean, imagine that the gravitational constant is not a constant, but a random variable. That's the first step. But it could even not be a random variable, but a quantum system with which we are somehow entangled. And whenever we look at the gravitational constant, it's somehow different. And we are just in one branch of the wave function. So maybe there is a big entangled state between our knowledge of what the gravitational constant is and how nature behaves, and we just perceiving one branch of this huge wave function, but actually there is no gravitational constant. So this is not, you're right, this is not captured by this. So here I'm assuming that a physical theory at least is a theory that we can write down on a classical piece of paper. But that's a very strong assumption.
I mean, one wants to say that at the very least you could write down a massive lookup table, you know, encoding every experiment you could possibly do and every result you could possibly observe.
Yes, but this still,
Okay,
for example, assume
that there are people who have experiences and those experiences.
Yes, so we are still
can be published
assuming that there's some reality and so on. So there are some assumptions which are highly, I would say, highly non-trivial. They sound strange, but the assumption is that there is some reality and there's something here. Okay, there was a question there. Aha, this is not an assumption. So, of course, the theory could be deterministic. It could be that given lambda, I mean, a deterministic theory would have the property that given lambda, there's only one possible value of x. And I'm not excluding that. I'm just considering the most general case. But thanks for asking that. So it's important that a theory that would just determine everything is, of course, one possible alternative theory. We will see that this is not a viable one, but it's one possibility at this point. And yes. So we don't exclude any determinism by this notation. The probability distribution would just be one that has a 1 in one position, or it would be a delta peak or whatever, if you're continuous. Okay, so that's the setting. But let's now, I mean, as I said, your point was very good. It's already an assumption to have some object like a variable, but I don't know how, I mean, there's no work in the literature that I'm aware of that, or very little work. I think there's one paper by Blumicode who explores that we are just quantum agents in the world and have to do a quantum theory about what is around. But apart from that, all the work that I'm aware of assumes that there is some classical object that describes nature. So,
question.
yes.
Historically, there were attempts to construct an alternative theory with hidden variables.
Yes.
Has it,
this is also included in that. That's also a good point. So hidden variable theories are such theories. So we will, and that's why our considerations will imply strong impossibility claims about hidden variable theories. So you can just say a hidden variable theory is just a theory. I mean, whether you call it hidden, this variable, or not, is not defined here. I didn't say whether it's I mean, it's not even clear what hidden means. It's something that appears in theory. In some way, you could also say the wave function is a hidden variable because you never observed the wave function in the lab. So this term hidden is, in my opinion, a bit confusing because it's not anything different from the nature of the wave function, because the wave function is clearly hidden from us. You don't see the wave function of this. Yes?
If we do physics, aren't we interested in laws which kind of universally hold? Like, or we try to find
yes.
patterns which are always true.
Yes.
That means they're always true for every one of us. So
yes.
Does that imply some classicality about the object?
Not necessarily. It could still be that we have different additional knowledge. So it could be that the rule is somehow universal, but the things, the objects you put into this rule are somehow observer dependent. But of course, we hope that there is a very simple rule like that. We don't want this to be a complicated object. But simplicity is an orthogonal kind of desired property of a theory than universality. But okay. Oh, what's that?
Just one
Yes.
brief comment.
Yes.
So, I mean, in the currently fashionable theories of quantum gravity, for example,
Mhm.
the Newton constant is actually a quantum variable,
Mm-hmm.
and what we measure is it's the expectation value of some quantum field.
Okay.
And decoherence
Yes.
is what
Mhm.
explains why we all think that the Newton constant has the same value.
Okay, that's one. Okay,
So, I mean,
that's.
that's
Mhm.
string theory,
Yes.
that's not
Yes.
some-
By the way, yes, I should mention that this would not be.
Yeah,
So this here does not exclude such a thing, because you can, of course, what you call lambda
yeah.
is not predefined. You could, of course, say
No, no,
G.
I'm saying
is
that fits into
yes,
your framework.
yes, yes. Okay, I mean that's not my framework. This, let me stress that this is just a way you can, or a formalism that allows you to describe a lot of the work that is currently being written about quantum foundations. Because I didn't now make any assumptions except that they're random variables, and random variables are, of course, a very general object. But let me now maybe give some examples, because it's very hard to think of these alternative theories without having something specific in mind. And there are many specific examples, and one of them is just what you mentioned, are the hidden variable theories that you may have known of. There's also things like Bohmian mechanics. This also fits into that. So in Bohmian mechanics, this lambda would actually consist of psi itself plus some additional positions of particles. I don't now want to go into Bohmian mechanics, but just mention that this is also something that would fall under this alternative theory. So all the statements we are going to make will apply in particular, for example, to Bohmian mechanics. And the other thing I should maybe mention before I move to the examples is that what we typically want as a minimum requirement is that the theory here is compatible with quantum theory in the sense that it would not lead to contradicting predictions. And the reason we want that is that we already did experiments and we know that quantum theory, in a certain regime at least, correctly predicts the experiments. So when we now look for alternative theories or consider alternative theories, we will restrict ourselves to theories that would not lead to a violation of experimentally verifiable facts. And by saying that, you could, of course, always argue we haven't tested quantum theory to arbitrary precision and so on, but I should already mention now that the statements we are going to make are kind of robust. So even if this is not precisely true, what I'm going to say, the statements will still be true, and so if the assumptions of the statements will be approximately true, then also the conclusion that we will draw will still be approximately true. So the stability allows us to say that we only have to verify quantum theory to a certain precision and not to arbitrary precision. Okay, so now what does compatibility mean? So and this is the first definition that I'm using. So we say that that this theory P, or theory that this probability distribution A lambda, and maybe I to now make a distinction, let me call it here A for the or maybe E for an extended theory or alternative theory, and this Q for quantum theory. So these are two different probability distributions, and they say that this one is compatible with PQ x given A lambda. If there exists a probability distribution P of x lambda given A and psi, which is that reduces, or that to the other ones, to PQ and PE. And what I mean by reduces to means formally the following. It means that if I drop a random variable, then I get one of the other theories. So in other words, you see, this would be a probability distribution involving both the variable of the alternative theory and the quantum state psi. And now I could somehow check whether if so quantum theory doesn't involve lambda. I will make an example for that, and this will, of course, clarify things. So what I could do is now to say, what happens if I ignore lambda and sum, so by summing over its value and not and don't do anything with the other value. So in other words, what this object here, so this is the quantum theory, this is this extension here, and the same should of course also be true for the other theory. So what I'm saying here is that there should exist a joint probability distribution. So I should be able to think about a scenario where at the same time someone describes this setting with quantum theory and someone else describes the same setting with an alternative theory. So let's say you are one of the, let's say, clever students who developed this new alternative theory. You have, and we are looking at the same experiment. And you will now ascribe a random variable lambda to it, and I will to a psi. So, and of course now both are defined at the same time, which means we have a joint distribution that involves lambda and psi. And we don't need, I mean, yeah. So, and now I'm saying that this joint distribution should of course be compatible with only the quantum prediction. So if you ignore lambda, if I don't look at the value lambda, I should retrieve exactly the predictions that quantum theory makes. So that's a necessary requirement to be able to claim that both theories can exist somehow at the same time, so that they don't lead to contradicting statements. Yes?
I see how you can throw away the lambda as you just
Yes.
did, but how do I throw away psi because it's on the conditional side of the P distribution? So I can't
Yes.
write the same formula.
So here you can actually choose. So your oh, actually I made here a mistake. Here should be a psi. Yes.
But I'm relating to the P minus P anyway. So what would be the corresponding equation to what you
Yeah. So here I would, in addition, have to take the. So actually, what we are okay. Here I would have to compute the conditional probability distribution. So one way to do it, I just did it now in a simplified way, but would be to define here a joint probability distribution, and then in both ways, whenever the joint probability distribution is defined, I can always define conditional ones. So the fact that I don't have lambda in the conditioning is not a problem, because if I have the joint defined, I can always condition by using these base rules.
But that means we don't
would be with removing one term?
Yes, 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 yes.
But then what you really mean is that there exists a joint distribution for all four variables.
Yes, I could define. I mean, it's not
It's
okay.
not sufficient to justify the condition.
So it's true that it would be kind of on this level be useful to have the joint distribution. It turns out for all the statements we are going to make, we are only using that. So this is kind of
That's 'cause you're
a
going
weaker
to
requirement.
something else is
Yes.
equivalent to quantum mechanics.
Yes. So we are not asking whether quantum theory is compatible. So it's kind of an asymmetric way of writing down the definition. And I was actually, when I prepared this, I wasn't sure whether I should give. So if I didn't write that, it would be a stronger definition.
Yeah.
But, and this would be maybe the pedagogically better way to do it. But in the actual theorems, we will only need that. But maybe you can think of it as do that, and then everything is symmetric. But this would be a slightly too strong requirement compared to what we need. But maybe it would, yeah.
I'm not sure what you mean by it would be a stronger definition. As far as I can see, with the type symbol, it's not well defined.
Aha. No, it's
Because I
yes.
just cancel out the side, I might have something like the exists this and the exists
Yes.
side, and then I can use that side to.
Oh, it's always so it's stronger in the following sense that whenever I have a joint distribution, I can always get all the conditional distributions from it. Of course, from a conditional distribution, I cannot, in a unique way, get a strong one.
We so far don't have a definition of compatible with the type symbol because we don't have a definition of what it means that px lambda condition x
Aha, yes.
to pe. That's what we can't.
So what you do is you just make both conditional. So you make Aha, you mean because of the psi is not defined? Yes. So you have actually here a liberty of how that's true. So here you still have liberty of how to define psi, or the probability distribution of psi, and it just has to hold for one of them. Yes. So maybe, I think you convinced me that for a pedagogical reason I should just not write that for the moment. And you should keep in mind that it can be slightly weakened. That's okay, now let me make examples. And the examples will probably also make clearer why I still chose this definition, or this way of writing it. But so the example is a very simple one. It's not, so I will, what I'm going to do is now not to give you a reasonable alternative theory. Like, I mean, for example, the Bohmian mechanics is in some way reasonable in the sense that it's a full theory, at least. So Bohmian mechanics is universal in the sense that every setting that you can describe in quantum theory can be described also with Bohmian mechanics. It's for other reasons maybe not reasonable, but at least it's universal. But what I'm now going to do is to just give you kind of a toy theory, which is extremely simple. But the toy theory is a toy theory because it only applies to one particular experiment. But it's just to illustrate this notion of compatibility. And the type of experiment I would like to consider is also a very simple experiment. We have here a source of particles. It's just a Stern-Gerlach experiment. Here we have a magnet or so. I mean, it doesn't matter so much, but the important thing is that we have here two detectors, and the detectors produce outcomes that we label +1 and -1. And we have here a preparation procedure. And now what you know from what quantum theory would now predict is that there is some internal object, or there's something like a quantum state. As I said, we don't see that quantum state, but we think of it as the state of the particle psi. So quantum mechanics tells us we should assign a state to the particle. And for that particular experiment, in order to predict the outcomes, so the outcome would be x, we don't need to know the full state of the particle, but only its internal degree of freedom, its spin. And then quantum theory would tell us that if psi is, for example, spin up, so we have two states, then then x is 1 with certainty. That would be what the Born rule would tell us in that particular case. And if this is down, then x is -1. I mean, I don't now write down the full rule, but we have seen the Born rule before. And in particular, and this is a more interesting case, is of course if psi is, for example, a superposition, then we know that both things occur with the same probability. So then we would have, so in this particular case, the probability distribution of x conditioned on, now there's not even an a, I have no knob to choose. So the x conditioned on the particular psi, so I just ignore the a for this experiment. Think of a as being a constant, is now 1/2. So what this means is that the probability of getting outcome +1 conditioned on this particular value of the wave function is 1/2. Okay, so that's what quantum theory tells us. That's true. Now what could an alternative theory be? An alternative theory could now consist of a different rule. And the rule could, for example, be the following. So lambda could be an element from a set which has two elements, up and down, for obvious reasons. And the rule would be that if lambda is u, then x is 1, and if lambda is down, then x is -1. So it's kind of a similar rule to quantum theory, but it could now be that the theory also defines or consists of lambda plus the wave function. So it could be that the theory prescribes that whenever the wave function is this particular one, so maybe I should denote it by psi s for the superposed wave function. So if I have this wave function, then I could define that then I will see this random variable lambda being in the u position with probability 1/2. So now what would that tell me? So this would now be a deterministic theory. Because whenever I know lambda, so lambda, in contrast to the wave function, can only take two values. So the wave function is, of course, a vector in a Hilbert space and can take this superposition. But lambda has only values u and d. So whenever I know lambda, I perfectly know what the outcome will be. So that would be a very nice theory, because it would always tell me exactly what I'm going to observe. Furthermore, the theory will be compatible with quantum theory. And this is very easy to see. You just have to do this calculation that I did before. Maybe I do it here. Oh. Huh? Can I erase that? You know, okay.
That didn't work.
Okay, maybe then I erase it anyway. Okay. So the rule before was that there is this, the outcome x conditioned on psi should be the same as if I sum over the possible values of lambda of the joint distribution of x and lambda given psi. So, you know, this was the rule we had before. Now we can easily verify that this is true, because in our particular case, let's just look at the particular case where the outcome is 1. Of course, the same will be true for -1. In that case, I have here to sum over lambda. So first of all, lambda could be up. So, but the probability, so I do it like that, so that lambda is up given psi times the probability that now x, I get an outcome x equal to 1 if lambda is up and I have psi. So this would be x given u plus the same thing for the down value. So here I just use this base rule to decide what's going on. Sorry, I should here always write down, and here 1 and 1. So this is just a decomposition of this probability here. I write this probability of x and lambda as the probability of lambda given psi times the probability of x given lambda and psi. And then I take this sum here over lambda. And you see, this one is by definition, this is what I defined here, is 1/2. And of course, I mean, the definition implies that the other value also has to be 1/2. So I have these things appear with probability 1/2. And this here has probability 1. Because if I'm up, I mean, that's this rule, if lambda is up, then x is 1. This is deterministic. And this then never happens, because if it's down, then x is -1, so this has probability 0. So what I get at the end is 1/2, which is exactly what quantum theory tells me. So this is the quantum prediction. So this is what it means for the theory to be compatible. So in other words, a theory that deterministically tells me what outcome I get can be compatible with quantum theory. That's important to know.
You just renamed X, though, right?
In some way, you could say I renamed X. So it's a very trivial theory. So let's therefore, or maybe first, after answering the question, I will move to a slightly more tricky example, or less trivial one. But you had a question before.
Shouldn't we have to verify it for all psi and give a
yeah.
lambda X for all
Yes,
psi?
we would have to, but as I said, this is only a toy theory, so it can only be applied to, I only define it for that psi. And actually, as it will turn out, I cannot make such a theory consistent for all psi, and that will be a theorem. But for the moment, at least on this level, it can be compatible. But you're, of course, right. This example is very trivial because somehow I renamed the outcome. But that's exactly what a deterministic theory does in some way. So any deterministic theory will always be just a renaming of the outcomes. But you're, of course, absolutely right. So let's now make it a slightly more non-trivial. And I could make it more non-trivial by just changing this part here. So let me now say, instead of saying that the probability that the outcome x is 1 given lambda, so this is 1, and given, for example, up, should not be 1. So before it was 1. Before I said whenever I have u, then the outcome x is 1. But I could now say, let's assume that this only happens with probability 0.9. And of course I could do the same thing for down. So I would say that px given lambda, maybe I should, sorry, need more space for that. So in order to, I also need to say what happens if lambda is down. And then I would say it only happens with probability 0.1. But however, I take the same rule as before, that lambda up given psi should have probability 1/2. So this is now a different theory, clearly. So the theory tells me whenever I know what the value of lambda is, I can predict the outcome of the experiment with 90% probability. This is a non-deterministic theory. So it's, for example, not the usual type of thing that was considered in Bell-type theorems, because in Bell, in the, let's say, basic version of the Bell-type theorem, you assume that the hidden variables determine the outcome. There are also other versions of Bell theorems, but okay. So what this tells you is that the theory is somehow better than quantum theory, because in quantum theory, if you know psi, you can only predict the outcome correctly with probability 1/2. But if the guy who invented this theory is much better, he can predict the outcome with probability 0.9. But the theory is still compatible with quantum theory. So what we have to change here is just, here is a 0.9, and here is now a 0.1. But you see, it still gives 1/2. So this shows that a non-deterministic theory, which is now a little bit, it's still a trivial theory, but a slightly more complicated theory, which is not deterministic, can still reproduce quantum predictions in the sense that it's compatible with it. And now the question, now to come back to the motivation, the question we are asking is it possible that there is such a theory that correctly describes nature? Could we hope to find such a theory? Or is there some fundamental reason why such a theory cannot exist? And the answer will be, yes, there is a fundamental reason why such a theory cannot exist. In fact, any theory that would give predictions that are better than quantum theoretical predictions would have some other very strange properties that we wouldn't know like to have. So here we are probably similar to complexity theoreticians. We are kind of not saying it doesn't exist, we just say then the world would be very strange. And that's maybe the type of statement. So, but this is important that you understand this example. So it's important that you understand that there can be theories on this level that would not immediately contradict quantum theory. However, the theories would be more informative, but may not be deterministic.
Well, I don't think that, I mean, to really make that statement in a physically meaningful sense, you would need it to reproduce all the predictions of quantum
Yes,
mechanics.
exactly.
And that's a lot harder.
Yes, I agree. And so that's why I only chose a toy example, because we will actually prove a theorem that this is not possible. So what you say is exactly the content of a theorem that we will see, that it's very hard to find a theory which is better than quantum. In fact, it's impossible unless I do something very strange.
Well, it is possible for all possible measurements on a two-level system.
Yes, for example, yes, that's right.
Three-level
So,
system is already a
but
problem.
already for a two-level system, I will have some very strange properties,
Yeah.
as we will
Yeah.
see.
Yeah.
Yes.
I think there ought to be a bit more elaborate scope, because what we ask here is it compatible with quantum theory? But in practice, what we actually need is compatible with experiments.
Yes, you're right.
Since quantum theory, like every theory, has more information than the finite state of experimental outcomes, so
Yes, you're absolutely.
what you are saying here
I
is
absolutely
not-
agree. What we would like to make as an assumption for when we are looking for alternative theories is that the alternative theory should still be compatible with all experiments we did. And saying that it's compatible with quantum theory is somehow a lazy way of doing that, because it would be very hard for me to define what it means to mathematically to be compatible with all experiments. However, it's indeed true that we will never need in the theorems that it's compatible with all of quantum theory. In fact, the theorem, when you look at it closer, will only involve compatibility with quantum theory in the regime where it has already been tested experimentally. So de facto, it actually means that we are just compatible with experiments. But of course, there's always this question that if you did, for example, an experiment with electrons or with photons, it's not clear whether if you did the same kind of quantum mechanical experiment with the same state but with different objects, with electrons instead of photons, whether it still has the same behavior. So in some way, this makes it extremely hard to define what it means. Or if I do the experiment here instead of in another lab, it could be different. So it's almost not definable what it means to be compatible with all experiments. And the only way I can imagine expressing that mathematically is to say it's compatible with quantum theory. But it's kind of, yeah, philosophically, one wants to say it should be compatible with experiments. Okay. Okay, now I've given this example. So now let's turn to the actual questions we want to consider. And so and now let me come back to what I said before about the one-to-one relation. So of course, there can be an alternative theory that may just make predictions which are essentially equivalent to quantum theory. And formally that would mean that we have here, so let's assume someone finds this alternative theory, but if he would present this alternative theory to me, and I would be able to find a function from here to here which is bijective, so it's somehow a one-to-one relation, then one couldn't really call that an alternative theory. Maybe still this variable is expressed as a completely different mathematical object. For example, here I have a Hilbert space, and this could be, I mean, you could think of this, for example, as a theory that turns out to be one where we talk about projectors instead of vectors. But obviously, that's equivalent to quantum theory, but it could be something more complicated. But as soon as I find a function from here to here, which is bijective, then it's kind of the same theory. It's just represented differently. So one of the questions we will try to answer is it true that for all alternative theories there exists such a one-to-one relation? Of course, I have to be a little bit more careful. So this alternative theory could just contain some redundancy. So for example, I could take the wave function here and add a random bit, and then I wouldn't have a one-to-one relation. So what I mean more precisely is that here I take an alternative theory which and build equivalence classes of all objects that lead to the same predictions. Because that's also, I mean, in quantum theory true, that if I have a quantum state with a different phase, that gives the same prediction. And so I kind of take the equivalence class of all vectors in a Hilbert space with different phases. And that's why it's sometimes useful to talk about projectors rather than vectors. So the one-to-one relation would apply to these equivalence classes of the objects we have in the theory. And that's indeed a question that has now recently been answered. So in particular, there is this theorem that I mentioned, the Ppr Theorem, which says, so this abbreviation stands for Pusik, Barrett, and Rudolph. And what they did is to show that at least in this direction we have a function. So their result is that for any alternative theory that satisfies certain assumptions, I didn't now state the assumptions, but you have to make some assumptions on this side, you can find a function such that the wave function is uniquely determined by lambda. There's also another argument that I will also show, which shows that there's also a function in this direction. So at the end, we know that there's a one-to-one relation. But for both statements, of course, we need to make assumptions about the theory. Because I could just, one alternative theory would be the theory that consists of a record of all possible probability distributions. Not probability, but of all outcomes that I will actually observe. That will be a deterministic theory, but as we will see, it will violate certain very natural properties that we would expect the theory to have. You had a question? Okay, you have a question after I stated the assumptions, probably. That's true. So the assumptions will all somehow have to do something with which are the parameters we can choose. Because what we will see is that theory that is too deterministic will not allow us to choose certain parameters. It will somehow also fix the parameters we want to choose. And here, if you have knobs like that, we somehow assume, at least in quantum theories like that we can compute the outcome for any position of the knob. And what we will find is that, or what we will take as an assumption is that the theory will also allow us to choose the knob in arbitrary positions. So if the theory is too deterministic, it will also determine the position of the knobs. And that's what we want to exclude. And that will be the type of assumptions we are going to make. I have to quickly check the time. Okay, we have now only 10 minutes, but let me start with the assumptions. Maybe I should, before going to the assumptions, because you may be tired, I should say a few more general things about that. And in particular, I should stress that the fact, okay, so maybe I will first write down the statement. So the type of statement now on a very informal level is that we will have the following. So for any alternative theory, so if whenever we have such a thing here, A lambda, compatible with quantum theory, so we want that it's compatible with x given a psi quantum, which is complete, and I will just say what that means, and allows free choices, and that is what I said now informally, and I will define that mathematically. So this is to be defined. That's why I make here star. There exists a function f such that psi is equal to f of lambda. So that's the type of statement we will show. This is now an incomplete description because I didn't define what complete means and I didn't tell you what free choices mean. And actually this Ppr theorem uses a different language, but I will show you that what they mean is also a certain type of free choices that they will allow. And this is actually true for almost all statements of that type, including the Bell type statement, that you can always see that as a certain way of defining that you can choose certain parameters independently of certain other parameters. And that's what free choice is going to mean. So here I also added complete. So the direction to go from here to here can of course not be true in general, because there is a very trivial theory that would violate it. A trivial theory would just be one in which I don't make any predictions, or in which kind of lambda is just a constant. There's no dependency on the system. I just make some random guesses. And so what I want, the minimum requirement is that the theory cannot be in a trivial way extended. So so it means, and I will also next time give a formal definition, it means that I cannot add a lambda prime such that I get a better prediction. So the theory should be complete in the sense that I cannot add any other parameter, so in order to improve the probability of correctly predicting the outcome of outcomes of measurements. So in other words, the statement is that any theory that is complete in that sense is essentially equivalent to quantum theory in the sense that the wave function is just a function of that. Now, okay, let me say two things. One is about the applications of that, and the other thing is about the implications to the, let's say, philosophical interpretation of the quantum state. But applications are, in my opinion, even more important. So why is it important to have this one-to-one relation? So suppose that it wasn't true. Suppose that there was a theory like a deterministic one, or let's say, suppose there is such a theory that makes better predictions. Then all the security proofs that we would have in quantum cryptography would essentially be useless, or at least most of them, all those that are based on quantum theory. There are also some that are not based on that. They're based on non-signaling correlations, but all statements we make based on quantum theory would be useless, because if there exists such an alternative theory, then it's reasonable to assume that an adversary may know the theory. And so if the adversary knows the theory, then of course all the predictions that the adversary makes should be described based on such a parameter lambda. And so indeed, if you look at the security proof in quantum, for example, quantum key distribution, then a basic assumption is that all possible attacks by an adversary are described within quantum theory. So if an adversary can do something that goes beyond quantum theory, then very obviously the security proof simply doesn't apply, because the very basic assumption that his attacks are described within quantum theory is not valid. So the statements of this type, that there's a one-to-one relation, is somehow absolutely necessary to have confidence in the claims that we make in quantum cryptography. Now you can ask, is this also true classically? But classically this is just trivial, because classically the classical theory already makes deterministic predictions. So clearly any other theory cannot be more informative. But here we have just seen an example of a theory that would clearly give better predictions. So it could be that, for example, in a quantum cryptographic proof, you somehow, let's say, the simplest thing is prove that a quantum random number generator produces random numbers that are not predictable by an adversary. So I could take this as the random number generator. But clearly, if the adversary has now, in quantum theory, I would conclude there's nothing the adversary can predict. The adversary may even know the state of the system, but clearly he cannot predict the number that comes out. But obviously he could if he had access to that theory. So that's one important thing you have to keep in mind, that this is not only something that satisfies philosophers, it's really needed for quantum cryptography. I don't see a way around that, unless you just make that an assumption and say there is nothing more complete than quantum theory. And the important other part about it is this is not saying that I'm assuming, so I still have to assume quantum theory is correct. So the correctness of the theory is something different. So even if quantum theory was correct, it could be that this thing here exists. And there is actually a nice example in cryptography of something going beyond quantum cryptography, or different from quantum cryptography, which goes wrong exactly because this relation doesn't hold. And maybe you have seen this example. It's maybe kind of funny to briefly mention it. So there's something called the Quiche Cipher. This is an example that maybe those who attended QCrypt, that I explained it there briefly. And it's an example of a quantum key distribution system, which is whose security is based on thermodynamic processes. Actually, maybe because time is almost over, and this is something that it's a very simple cipher and doesn't require much thinking to see what's going wrong. I'll maybe end with that instead of going into the technical details of that. And it will also illustrate very nicely why we need these statements. So actually the example really shows that it's absolutely necessary to have them. So what is this cipher, or this Quiche quantum key distribution scheme, or not quantum key distribution scheme? The idea is that you have a line, an electrical wire, between two parties, Alice and Bob. And now here you have a switch, and there are two resistances that you can choose. A small one and a large one. And they are grounded. And the same is, you have the same infrastructure on Bob's side. So there's also a switch with a small resistor. So you can either connect it to a small resistor or a large resistor. Okay, what will happen? So if you learned something about electricity, you would say that nothing will happen because these things are grounded, so there will be no current. But if you go a little bit more into thermodynamics, you will learn the following, that if there is a resistance, let's call it R small and R large, and here R small and R large, then you will see that the noise, so there will always be fluctuations on this wire. So whenever you measure the current here going through the wire, it will of course on average be 0 because there's no voltage applied here. But there will still be small current fluctuations. So sometimes there will be a little bit current going to the left and sometimes to the right, and you can measure that. And this is due to thermal fluctuations because the electrons move in the wire. And it turns out that, so here you can measure fluctuations. And now let's call them F. And now it turns out that F depends on total resistance. And now imagine the following. So the scheme is now the following. Alice and Bob randomly choose switch positions. Now the total resistance will be the same independently of whether Alice chose RS and so we have, or let's write down the 4 combinations. So we have one combination where both chose the small one. We have one where Alice chose the small and Bob the large one, and vice versa. And then we have the one where both chose the large one. And now the fluctuations will be, so here we have identical fluctuations, because obviously if these resistances are chosen to be the same, I mean RS and RL, they will sum up to the same number, whereas here we will have different fluctuations. So now what Alice and Bob do, they randomly choose switch positions and measure also the fluctuations. So they can measure fluctuations here as well. And of course the adversary may also measure it. And whenever you have a fluctuation corresponding to either that one or that position, so that will lead to different fluctuations, you would just discard the event and start again. So you again choose random positions, and you only keep those where you are in this regime. And that you can easily test by measuring the fluctuations. But if you are in that regime, someone sitting here in the middle cannot distinguish these 2 positions. You just have, you know that the total resistance was RS plus RL, but you don't know whether it comes from Alice choosing RS or Bob choosing RS. So these are the instances which you keep and use as a key. So Alice would just say this is called a 0 and this is called a 1, and Bob does the other thing. He calls that a 1 and that a 0, and then they establish a key using that. And now there is a security proof, and the security proof uses this law that says F depends on the total resistance, and says, okay, well, if the adversary measures that, then clearly there is no way to distinguish these 2 cases. And there is something obviously wrong with that, that you can see. I mean, some people apparently don't see that, but the obviously wrong thing is that this law here is not a complete law. It's a correct law, but it's not complete. And this is exactly what's going on here in this question. So if you would now say that this law here is like established quantum theory, and now we have a security proof that is based on this law, and the security proof is correct, and there's nothing mathematically wrong with that. But the problem is that there is another theory, and this theory would just have more parameters. It would not only look at the resistance, but it would also, or not only the fluctuations, it would also look at microscopic degrees of freedom, maybe kind of certain individual electrons, or how, for example, these fluctuations evolve over time. And if you take into account these additional parameters, that would be a lambda. Then you may be able to make better predictions about measurable outcomes. And that's, of course, the case here. So there's no reason to believe that the theory is complete here. And it's not. So indeed, because it's at the end a classical theory, you could indeed measure individual electrons here, and from the measurement of individual electrons, conclude whether Alice or Bob chose RS. But this example illustrates very nicely that even if you have a correct theory, so there's really nothing wrong with this formula. So even with a correct theory, there's no good reason to use it in security proofs. So what we need in security proofs, and there is no way around that, is to have a statement that the theory you use is also complete. Complete in the sense, in exactly that sense, that there cannot be an alternative theory which is different from that and would provide more information. So that's why this is really very important for applications.
What is the precise measurement that you choose to distinguish between those 2 possibilities?
Okay, this is a good point, because I will now not give you an answer what is the precise measurement. The point is, it's clear that it exists. I mean, there's still an ongoing debate. You can even follow that debate on the archive between Charlie Bennett, who tries to convince the inventor of that scheme that his scheme doesn't work or is not secure. And of course, whenever Charlie proposed a particular measurement, so first he, for example, proposed to use a time series of things. So you would just, instead of measuring so these fluctuations refer to average fluctuations over time. What you could do instead is to measure how the fluctuations, like you could measure fluctuations at 2 positions and then see how they are correlated. And Charlie could show that you would see in the correlation who has the smaller resistance in the time dependent. But then, of course, the guy who invented the scheme just invented some countermeasure to prevent that. But it's clear that the theory will never be complete. You can always do something against it. So there will, but the point is, I mean, it's now, my point is not to now give a specific attack. My point is to say that in order to have a security proof, you need to prevent all possible attacks, and this is only possible by having a statement that tells you that your theory is complete. Okay, there was another question there.
Yes, so as I have understood what you are going to show, it doesn't seem to exclude that either, because there is like this this arrow does not seem, from what I've seen so far from the definition, seem to exclude that there might not be that if we don't expand the range of A, that we might get more things.
The range of A.
Yeah, there's this capital A,
Mm-hmm.
the knob. So
Mm-hmm.
what if we, so all your definitions were like relating experiments with the same knob.
Aha. Yes.
And what if I have a knob which which goes out of range, and there I suddenly get things, because this is what you have done here.
But this.
Charlie actually.
No, I think the important thing is that, of course, the quantum mechanical proof of security will not be restricted to certain particular knob positions.
It will be restricted to all knobs that exist in quantum theory. So perhaps they are like
Yes.
the same knobs,
Okay.
you get the same stuff.
Yes.
Perhaps
So,
all knobs.
okay, that's a good point. So the question is also, what do I really mean when I say a theory is at least correct? And correct has to be interpreted that I can apply it to everything that exists. It may not give complete statements, but at least, I mean, even if you invent a new, let's say if you have a knob and now it goes out of range, then it shouldn't be true that now suddenly it reaches a range, or somehow the knob is in a position where quantum theory is not applicable. So correctness means that quantum theory should always tell me something. Maybe it tells me something very weak. Maybe it tells me that in this case I can only make a prediction of half-half of what the outcome is. So you're right that I have to make sure, and whether you call that now correctness or completeness is a different question, but you have to make sure that the theory already encompasses all possible experimental parameters that you can choose. But quantum theory doesn't contain restrictions. So quantum theory doesn't tell us that if the voltage is larger than that and that, we are not allowed to apply it. So quantum theory just tells us for any possible, essentially, any possible configuration, we can make a prediction. Of course, if you find something which is so strange that you cannot describe it as a knob, that may be problematic. But then we probably don't care about cryptography any longer. But you're right. I mean, there is some subtlety in what we do here. But that's already a point in a problem in the current definitions, that you say that we don't know whether the Hilbert space has finite dimensions, or we go to all possible dimensions and so on. But everything that can be described within quantum theory is captured by the current proofs. And the question is now, within the things that can be described in quantum theory, which seems to be everything, could there still be something that describes it more accurately? And that is excluded by these statements.
You're going to define these computers and so on.
Yes. So everything that I said, so today's lecture was kind of to give you an overview of what, or why this is relevant also, and what the statements are. Now we will tomorrow make all these things mathematically precise. I will show theorems, and then I will hopefully also have time to show you a proof of the theorem. Maybe I will only do one direction. So it may be that I only show you the direction from here to here, why there is a function from here to here, but there is also a function in the other direction. Okay, so I think this is enough for today morning, and it's time for lunch. Yes, thank you.